Hello, everyone, and welcome to the final series of talks here at the 2020 Virtual Heidelberg Laureate Forum. I am Dr. Tom Crawford. I'm a mathematician at the University of Oxford, and I also do lots of things on YouTube. So I have my own channel, Tom Rocks Maths, and I work a lot with Numberphile, just in case you thought I looked vaguely familiar. It gives me great pleasure to introduce our first speaker for this evening's session, Professor Barbara Liskov. One of the first women to be granted a doctorate in computer science in the US, which was at Stanford in 1968. She has since worked at MITRE Corporation and is now based at MIT. Professor Liskov was awarded the Turing Award in 2008 for contributions to practical and theoretical foundations of programming language and system design. And in this talk, she will discuss our current understanding of abstraction and modularity and the research that got us where we are today. Professor Liskov, over to you.
Okay, thank you very much. As you just heard, I'm going to be talking today about programming methodology. And I got into this field in 1970. So as you just heard, I got my PhD in 1968. But when I went to look for a job, I wasn't offered any good job as a faculty member. And so I went to work at the MITRE Corporation as a researcher. I had actually worked at MITRE earlier between my undergraduate and graduate education. Then I was a programmer, now I was doing research. And this actually turned out in the end to be a really good thing because at Stanford, I got my PhD in AI. And I wanted to switch into computer systems. And by working at MITRE, I was able to do research in systems and devote full time to it without having to think about also teaching at the same time. So my first project at MITRE first involved developing a machine architecture and then an operating system. And then about 1970, I was asked to look into the software crisis. The software crisis probably doesn't sound like something you've heard about, but this is what it was. In 1970, we didn't understand how to build programs that worked. And as a result, software development efforts failed. And it was very common at that time, and actually right in through the 80s, to pick up the newspaper and discover that company such and such had spent millions of dollars and hundreds of man years. And in the end, the entire software system had to be discarded because it didn't work. So clearly there was a serious problem here. And so I was happy to start working on this. I'd never known about what was going on in this area. This is the area of programming methodology. So of course I did what any sensible person does. I started by reading the literature. And what I discovered is that people were concerned about two different but interrelated problems. One of them having to do with how to design software systems, and the other one about what should the structure of these programs be. There were many interesting papers that I read at that time. Today I have time only to talk about one of them, and this is a paper by Dave Parnas. Dave was interested in the question of what should the structure of programs be. And in another paper that he published at about the same time, he said, we know we want our programs to be consisting of modules, by which he meant just pieces of code, but we have no idea what these modules are, which give you an idea of how bad things were at the time. This paper was about modules also, and had to do with the fact that we didn't understand what their interfaces ought to be and what should be included in them. So what I'm going to do now is jump to the present and talk about our current understanding of modularity. Today, we understand that a program is a collection of modules, just like we were looking for then. But we understand much more about what this is. We understand that a module is a thing that has an interface, and that interface is described by a specification, and the purpose of the specification is to completely describe what the module does, what you can expect from it if you use it. For example, if we have a sort routine, the specification would say it takes in an array of integers as an argument, and when it returns, the integers in the array have been rearranged so they're now in increasing order, something like that. Now, once you have this notion of a specification that's a complete description of behavior, then you have a way of talking about the correctness of a module's implementation. It's correct if it meets its specification. And as you do that proof, which might be formal or informal, you may discover that that module's implementation makes use of some other module, but that's okay because I can just use the specification of that other module in this reasoning process. I don't have to look at the code. And therefore, what I have here is a way of doing local reasoning module by module, and yet at the end I could understand the correctness of an entire huge system. And this all works beautifully, provided we follow one very important rule. This notion of local reasoning, which is so important, works only if modules depend on the specification and not on any details of the implementation. Obviously, if outside modules can look at what's inside, then if I change the insides, things are just not going to work. Okay, so that was then. But if I go back to 1970, we knew we wanted modularity and we understood its benefits. We understood local reasoning was crucial. We also wanted independent development where different programmers could take different modules and yet in the end they'd be able to work together. And we also wanted modifiability, which means that if some module isn't working as well as we'd like, we could rip it out, put a new one in its place, and still the program would continue to work. But we didn't know what it was. And furthermore, there was only one thing we had to play around with that seemed like it might be a module mechanism, and that was procedures, like the sort routine. And they simply weren't powerful enough. I mean, a file system is obviously an important notion of a module, but it's not a procedure. And furthermore, at that time, the complicated connections that Parnas was talking about were obviously a problem. Okay, so I read all these papers and thought about them. And I realized that in my earlier work at MITRE, when I was developing this operating system, it was the Venus system, I had actually invented a design methodology, a programming methodology. I was concerned, I had a small team of programmers, we had to implement a time-sharing system, which was really a challenge at that time. And I was concerned about how we were going to do this and how we could break the program up into pieces and not have things get in each other's way. And a common strategy for building systems at that time was you had a large collection of global variables, you had different pieces of code, and this code interacted via the globals. That was the complicated connections Parnas was talking about, and it was a mess. And what I decided to do was to get rid of the global variables by breaking the system up into partitions, and each partition owned a part of the global state that was local to that partition, and it provided a bunch of operations, and the rest of the implementation would never interact with it by going after its global variables inside, but instead would just call the operations. So this was a novel idea. As I showed you, I wrote it up and published it in 1972. Okay, at this time, I moved from MITRE to MIT. What happened was I had written a paper on the Venus system, and it was a prize paper at SOSP, which is the top systems conference. And so I gave a talk there, and unbeknownst to me, because I wasn't paying attention, something called Title IX was about to pass. And this is a law in the United States that had to do with access of women to athletics in colleges, but had the effect of opening up a lot of stuff for women. And as a result of Title IX, some universities were now interested in hiring women on their faculty, and MIT was interested for sure. The president of MIT was interested. And the chair of my session at SOSP was a faculty member at MIT, and there were several other faculty members in the audience. And as a result of what happened at SOSP, I was invited to apply, and so I moved to MIT in 1972. At that time, there were 10 women on the faculty, a faculty size of nearly 1,000. So this was a really good time for me to move. The glory of being at a university is that you get to decide your own research direction. Of course, that's also the curse. You have to know what you're doing. And I had at this point a research problem that I was really interested in, I wanted to work on. And so I went to MIT knowing what research I wanted to do. And what I was focused on in the fall of 1972 was this question: how can these ideas about modularity in design be applied to building programs? Because what I had discovered was that there were many good papers and they would describe some idea they had about how to structure a program. And you would read the paper and you'd say, oh yeah, that's really, the right way to go about it. But when you moved away from those papers and tried to apply these ideas to your own system, the whole thing fell apart. You couldn't figure out what to do. So I was looking for something to bridge this gap, something that would make it more obvious what you ought to be doing when you were designing so you could come up with a good modular structure. And sometime in the late fall of 1972 or early in 1973, I had this wonderful idea. I all of a sudden saw that I could think about partitions as data types. So it might sort of seem obvious in retrospect. I mean, after all, it looks kind of like an object. It's not really, a partition really isn't an object. It's really all the code that's needed to implement a data type. So there'll be some constructors in there for creating new objects, as well as the operations that you can call on the objects themselves. But the fact that you have this piece of code that provides objects, operations, and hides its state, that was what was the critical thing. And I saw how I could make that jump to data types. And I knew right away this was really important. The reason it was so important, there were really three reasons. First of all, it links modularity to design. The way we design is by inventing abstractions. So for example, if you're thinking about an Amazon-like system, you'll think about, oh, I want a shopping cart. Oh, I want inventory and so forth. You're really thinking about big pieces of the system, and these are often data abstractions. Furthermore, programmers understood about data types. It's true that at that time, the languages provided just a small set of them and you couldn't invent new ones, but these were nevertheless abstractions and programmers were perfectly comfortable using them. And this meant that they would be able to invent new ones. In fact, as soon as you think about the fact that you could invent them, all sorts of data types that would be interesting immediately come to mind. So it was clear this is going to really be a big help. But to make it all work, we needed a programming language support. So I started to work on that problem. And I did this jointly with a person named Steve Zillis. Steve was a graduate student at MIT at the time and also an employee of IBM. And he had some similar ideas. So we thought we'd work together and see if we could figure out what it meant to have a programming language that supported abstract data types. And again, we read the literature. And since time is short, I'm going to talk just about one paper. And this is the paper by Jim Morris called Protection in Programming Languages. And what Jim was concerned about was the question of how do you get independent reasoning for modules? So I've sort of already talked about this, but that's the modern understanding. A lot of that is coming from the work that Jim did. And what he said was, code outside the module must not modify the data module managed by the module. That's clearly important because if the code outside could modify the data inside, there's no basis for independent reasoning since you have no control over what's going on. But then he went on to say, it shouldn't even observe it. And that's a little less obvious, but the reason you want that is because of this goal of modifiability, where you can re-implement a module, replace the old one with the new one, and the rest of the program will continue to work just fine. Jim then went on to say he didn't know how to make this, how to enforce this. And he proposed a mechanism kind of like cryptography, where the module has a secret key. Every object that goes out is encrypted, and therefore outside you can't muck around with the objects. And inside, when the object comes back in, you can decrypt it and continue with your work. And clearly that was a non-flyer since it would be much too expensive in practice. So Steve and I read this paper, many others, and we worked all the time on this, many months. And by the end of the summer of 1973, we had come up with a proposal for a programming language that would support data abstraction. It appeared the following year. And then I took the obvious next step. I decided to develop that programming language. And what that paper said was, basically data types, sort of like we understand them today, a set of objects, a set of operations, and the important rule, you can only use the operations to create and modify and use the objects. And there was also a sketch of a programming language. Okay, so now it's the fall of 1973. I started to work with 3 young graduate students who had joined my group, and they became the principal designers of the CLUE system. Now, it's obvious why I should do this work, but I just want to go through the rationale. The first point is a programming language is a mathematical object. It has precise rules. You can't get by with a programming language where the semantics is not well defined, because then you would never be able to write a compiler or understand how to write programs in that language. And having precise rules was very important. I felt that part of the problem with those earlier papers is they were fuzzy, and that was why it was so hard to apply what was going on. The other thing, though, is a programming language is a tool, and it needs to be a tool people want to use. And so by designing and implementing a programming language, we got to evaluate very important aspects of it. Was it convenient? Was it easy to use? Was it expressive enough? Could programmers write the programs they wanted to write in a relatively straightforward way? And also, did those programs have good enough performance? All of these were very important questions that we had to answer. I don't have time today to tell you much about CLUE. This is just a very high level picture of what's in it. First of all, it contains something called clusters. This is where the name CLUE comes from. And these were very similar to classes. They were the way that we implemented data types. But then it turned out we had to do a whole bunch of innovation, because programming languages today are not like what they were when I did this work in the 70s. We had to invent an iteration mechanism, because many data types are collections. And if you collect together stuff, then you're obviously going to want to be able to iterate over the set or whatever it is that you invented. We also had to innovate an exception handling, because languages that in those days didn't have good or any exception handling mechanism. And most importantly, we had to figure out how to do polymorphism or generics. So when you have programming languages that don't have very many types and you have no way of adding new ones, then the need for generics is not so clear. I mean, so what if you have to build 2 sort routines, one for integers and one for floating points, something like that. But as soon as you start to think about a programming language where programmers can invent new data types, the need for polymorphism is obvious. And there were no languages with polymorphism, so we had to invent that too. Okay, so I finished this work in the late 70s. And at that point, I actually started working in distributed computing. And I don't have time today to talk about all the work I did there, many interesting projects. But I also continued to work on programming methodology right through the 80s. And I'm going to talk about one thing further that I did in that area. The work in programming methodology was sort of continuing to flesh out this, what is design, how do you reason about correctness, and so forth. And mostly this was done in the context of a course that I developed at MIT. Okay, so I'm going to talk about type hierarchy. So I was asked to give the keynote for UPSLA, the Object-Oriented Programming Language Conference, in 1987. I think this was the second year that UPSLA was in existence. And I decided this was a good opportunity for me to look into what had been happening with Smalltalk. And there was a lot of work going on in the Smalltalk style of building programs, mostly on the West Coast, whereas the abstract data type work was mostly on the East Coast. Things were not as interconnected then as we think about them being now. So Smalltalk was based on Simula 67, and it provided an inheritance mechanism where a class could define a certain representation for its objects, and then a subclass could extend that and add some extra operations. And I wasn't particularly interested in the implementation part of inheritance, but I discovered in reading the papers that people were also thinking about the semantic interrelation between the class and the subclass. The idea was the class would define a type, and then the subclass would define a subtype, and they were trying to understand what this meant. And I discovered they really didn't have any idea what it meant, because I read a paper, this is one of many I read, in which they said that stacks and queues were both subtypes of one another. And this could be true in a syntactic sense, because you could say, I've got an add element and a remove element, those two methods with the same names, and syntactically it might all look okay. But semantically, it's not okay at all, because if I wrote a program that expected a stack and I was passed a queue instead, my program very well might not work, because when I dequeued something, or rather popped something, I would get not the last thing added, but the first thing added. So this caused me to invent what's come to be called behavioral subtyping. And in my talk at UPSLA, I said, basically what I have written on the slide, that objects of subtypes should behave like those of supertypes if used via supertype methods. And I emphasize behavior here because I really was thinking about specifications. I was thinking about the subtype has a specification, the supertype has a specification. You ought to be able to prove that this behavior was satisfactory, but you only had to worry about the supertype methods because you're worried about the code that expects to get a supertype object is passed a subtype object instead, but wants to use it without noticing that it's any different from the supertype. There was a paper published based on my talk at UPSLA. It came out as in the SIG plan notices in 1988. And then in the early 90s, Jeanette Wing suggested to me that it would be good if we came out with a more worked out definition of what this meant. And that was published in Topless. This thing that I invented came to be called the Liskov substitution principle. I did not invent this name. I didn't even know there was such a thing until the early 90s, when I got an email from someone saying, can you tell me whether such and such is a correct interpretation of the Liskov substitution principle? And then I discovered there was lots of chatter about this thing that I had invented going on. Okay, so I just want to conclude with one other thing. When I got the Turing Award in 2009, I discovered that modularity based on abstraction is the way things are done today. What I discovered was that my students had no idea there had ever been a before. This was so ingrained in the way that people thought about programming that it had come to be the thing, and it had always existed. And in fact, my husband was online every day looking at the chatter on the internet about my receiving the award. And one of the comments he came upon said, why did she get this award? Everybody knows this already. And I'm sure that was not intended in a nice way, but in a way it was a huge compliment to my work and the work of many other people, because when we did this work, this was not the way it was. But by now it had come to fruition, and it really is the way programs are built. Thank you. That's the end.
Brilliant. Thank you very much, Professor Liskov. Fantastic talk. I'm going to give you I think everyone else, I'm giving you a round of applause, which I know you can see, and hopefully everybody else, I'm sure, is also applauding wherever they may be. Very enjoyable talk. Thank you. We now have a little bit of a time for some Q&A, about 5 minutes or so. And I've already got a question come in from Maria. So I think we'll kick straight. I've got loads of questions as well, but I think it's only fair that we'll allow the audience to kick us off. So Maria has asked, was CLU, C-L-U, a precursor of OO programming languages?
So I think the fair answer to that question is that OO programming language came from two places. They have adopted a structure for implementing programs that's much more like what came out of Smalltalk, using classes and subclasses. But a very important part of this also is the notion of data abstraction with specifications separating behavior from implementation. And the two together are what you need, because you need to be able to think about your data types abstractly. And you could have implemented with clusters, but we implement it more with the hierarchy mechanism.
Awesome. Thank you. I hope that answered your question, Maria. And we've got another one, which has come in, which begins, I'm just trying to strain to see this. I'm a mathematician who programs, not a computer scientist. Short question, what do you mean by an interesting data type?
An interesting data type. It's any.
I wonder if you've got maybe an example or something for a let's say for the mathematicians amongst us, myself included.
I'm not sure I can answer the question for a mathematician. Right. An interesting data type is anything that makes sense for the application that you're working on. So I tried to give you an example for an Amazon-like system where you would, have a shopping cart or an inventory or something like that. These are just data types that you can interact with that make sense for your application domain. And for a mathematician, these might be mathematical objects. I don't really know, matrices probably, other stuff like that, whatever works for your application domain. And I think if you start to look at, programs that do fast Fourier transforms or a lot of the recent machine learning stuff, a lot of the recent robotics stuff, what you'll see is lots of very interesting data types that are related to those fields.
Brilliant. And that actually leads on to a question that I had, which I know a lot of my students have certainly asked me in the past, especially the ones who do both maths and computer science. So from your experience, having of course worked in computer science, are there any particular areas of mathematics that you think are, that appear a lot or that would be very useful for someone who was working in maths who maybe wanted to make that switch over to computer science? Are there any particular areas that it would be useful to really be, understand well to sort of help that transition?
Well, I did my undergraduate degree in math. I've always felt that math training was very important. I mean, actually, when I described the way that you prove the correctness of a large software system by working module by module, I think this is very similar to using lemmas and proofs. Each lemma is module X implements its specification, and then you use that lemma in proving other modules that use the lower level module and so forth. For me, I think discrete math has been what mattered. And, the notion of proofs and stuff like that. But there's a lot of areas of computer science where non-discrete, where the other continuous math matters. And maybe that's coming more and more into its place. So you think about robotics, things are moving in real time and real space and stuff like that. So I would say, I wouldn't worry about it. Whatever kind of math you like, get a good grounding in math. In any case, it's going to be good for computer science, whatever you end up with.
It's really reassuring to hear you say that your original degree was in math as a, as a mathematician myself. Fantastic. Okay, and then something else as well that sort of came to mind as I was listening to your talk was you sort of gave us a very nice history of sort of your journey through the various things you'd looked at. Yeah. And I was just wondering if you had, or if you could possibly sort of describe a little bit how the subject has changed over the last 50 years, sort of, of course, not perhaps everything, but if you've noticed any major shifts or major events that have happened within computer science over the time you've been working in the field.
Well, there have been huge shifts. So one of the things I said was, I told you a huge shift. I said, we didn't know how to build programs. Now we know how to build them, right? That's a huge shift. I started working in distributed computing in the late 70s. At that point, we had a little thing called the ARPANET, which connected a few universities and research institutions. We didn't know how to build distributed programs. Now we have Google and all those other internet services. So another huge shift was, happened in the 90s when all of a sudden, instead of computers being limited to researchers and some businesses that did data processing, all of a sudden, everybody was on the internet. And so that's another huge shift. And then another huge shift that's happened is the way AI works. It used to be that machine learning is very important, but we used to do it very differently than it's being done today. So I think, one of the things that's been nice about computer science is it just keeps moving along. was something else I was going to say, but it slipped my mind. Anyway, very, very dynamic, a very dynamic field.
Absolutely. Thank you. Right. So I think that's just about time for this particular session. So again, thank you. Thank you so much, Professor Liskov, for sharing your knowledge with us all. Thank you to everyone for joining us. And of course, the talks will continue. I am personally going to jump over to the next session. So I strongly recommend, if you're watching this, you also do that. And again, if we can just thank Professor Liskov one more time with our virtual round of applause. And we'll see you all soon. Thank you.
Okay, thank you. And I just want to say people can send me email if they have questions. It's fine.
Brilliant. Thank you.
Bye-bye.